Good morning. We've been studying context-free languages, and now we will study a new kind of automata called push-down automata. So far we studied finite state automata, and we showed that they exactly recognize regular languages. We also saw that there were languages which were not regular. For example, there were context-free languages generated by context-free grammars, and there were languages which were not even context-free. We showed the existence of such languages by checking them using the push-down automata. So the question that arises is, what kind of automata will recognize these languages which are richer than regular languages? For example, what kind of automata will recognize context-free languages or the other languages that we have seen? And in order to do that, we augment the mechanism of finite state automata with some sort of memory. So the automaton is able to remember something about the part of the word it has seen so far, right? So in finite state automaton, what happens? Let us see that a little bit. In finite state automaton, we have the finite state control. The automaton is in some state, and it scans the input tape left to right. It reads the current symbol. Based on the current state and the current symbol, it will make a transition and decide what state it goes to. So for DFA, deterministic finite automaton, the transition looks like this. It depends on the current state P in which the automaton is, and the current symbol being read, which is A3, right? And the result of this would be something like you will go to state Q, right? That is what will be the result. And of course the current symbol will be consumed and the head will move one position to right. And we had richer models of epsilon, NFA, etc. Now in order to recognize, and such automata will recognize regular languages. In order to allow them to recognize richer languages, we will enrich the automaton with some kind of memory, right? And this memory takes different forms. So for example, in counter automata, this memory is of the form of some sort of counter, and this counter may, for example, remember the number of A's read so far, and every time a B comes, you can check off the counter, decrement the counter. Every time an A comes, you can increment the counter. If at the end of the word the counter has got value 0, then you know that number of A's is equal to number of B's. So you can recognize some sort of language with equal number of A's and B's using a single counter. So you can enrich the memory by using some counter, and this gives us counter automata, right? Then we can have a memory which is an infinite read-write tape. So apart from this input word, there is a scratch memory tape where you can write symbols and read symbols, and you can go to different positions. So infinite tape, and we'll see this later in the course, and this will give us Turing machines. Yet another kind of memory is what is called the stack memory. Okay, and a stack memory is what is drawn here. So let me explain to you what is stack memory. In stack memory, what we have is that the automaton, apart from reading symbols from input alphabet sigma star, there is a tape alphabet called gamma. Okay, so I have tape alphabet. Let me write it here. Tape alphabet, not tape alphabet, sorry, stack alphabet. I apologize. Stack alphabet. So there is a set of symbols, which can be pushed onto this memory called stack. Okay, and this is an unbounded memory where arbitrary number of symbols can be stored, right? And there is a distinguished symbol, bottom of stack symbol. So this occurs at the bottom of stack, and this stack is like stack of plates, it's like this, And what the kind of operation you can do on a stack of plates is, if you want to examine, whether the plates are clean or dirty, you can only look at the top plate. If you try to look at something deep inside, the whole pile will fall. That's not allowed. So the only operations allowed are, you can examine the top of the stack, then you can remove the thing from the top of the stack. It's called popping, and you can add some new plates on the top. So a composite operation may be, you can always remove one plate from the top, and you can add a sequence of plates at the top. So that is what you would have. You will remove that topmost stack, and you will add these things there. Right? So this is the kind of operations that you can do on stack. And our stack will not contain plates, it will contain symbols from this stack alphabet, right? So our finite state automaton basically has following things. Let me show you this thing. It has a finite set of states. Okay, it has an input alphabet, so your input word is going to be from this alphabet, and it will be loaded on the input tape, and you will scan this left to right. Okay, and you got a stack alphabet. These are the symbols which will be stored onto the stack. There is a start state in which the automaton starts. There is a special symbol which lies at the bottom of the stack, right? So this is called the initial stack symbol or the bottom symbol. Okay, and then maybe you have a set of final states. And transition table consists of a list of transitions, right? What does each transition look like? Well, the transition looks like this. What can an automaton do? The automaton can be in some current state P. It may be reading some current symbol, which is A3, and it can also look at what is on top of the stack. So currently A is on the top of the stack, and a transition rule will look like this. If my automaton is in state P, and if I am reading currently an input symbol called A3, and if at the top of the stack is a symbol A, which is what happens in this case, then I change my state to Q. So I change P to Q, and I replace this symbol A on the stack by a sequence of stack symbols B1 to BK, right? So B1, B2, BK. And so the new position, what will happen on taking this transition, this is the configuration of the push down automaton in which this transition is being taken. Then what happens is, because you are looking at symbol A3 and you are in state P and the top of the stack symbol is A, you will consume this A3 and the head will move here. Okay, you will change this state from P to Q. Okay, and you will remove this A symbol, the other symbols will remain as they are. So you will have bottom B, C, B, that does not change. This A is replaced by B1 to BK, with B1 occurring at top. So you will have B1 here, you will have something, and BK here. So this string A, this symbol A is popped, and instead this sequence of stack symbols B1 to BK, which is specified in the transition, is pushed on top of the stack. So this becomes the new stack. This is the kind of moves that occur in a push down automaton. The other kind of move is, you don't need to consume a symbol A. You can have P epsilon A. You can make a move like this, Q B1 to BK, right? So these are the two kinds of moves which are allowed in a push down automaton. So what is the transition function? It says on the current state Q, looking at either some symbol from sigma, which you specify, or an epsilon, and a stack symbol which you are seeing currently, top of the stack symbol, you go to a new state and you pop the top of the stack symbol and replace it by some sequence of stack symbols specified in my transition. So my transitions are going to be of two forms, it's going to be P A some B goes to Q B1 to BK, or they are of the form P epsilon B goes to some R B1 to BM, right? Some other sequence. So and our automaton is non-deterministic. For the same PAB, there could be two transitions. So I could also have a third transition called PAB, So now, under same conditions, this transition can also be taken, this can also be taken, and this may go to some state R with some symbols B1 to Bm, right? So I can either non-deterministically take this transition or this transition, and of course there can be also non-deterministic between a transition with a letter and an epsilon transition, right? It starts from the same state. So our automaton is non-deterministic, and a transition table is a list of transitions like this, right? So the full definition of a non-deterministic push-down automaton, I will just use PDA to denote non-deterministic push-down automaton, is that it consists of a set of states, an input alphabet, a stack alphabet, a start state in which the automaton starts, an initial stack symbol or bottom of stack symbol, a set of final states, and a transition relation, which is a list of transitions which look like that. Let me give you an example. So here is a PDA, and it has got a single state. So its set of states is Q. Its input alphabet is left bracket, right bracket. Its stack alphabet consists of the bottom symbol and the left bracket symbol. So on the stack, I will have something like bottom, left bracket, something like this. My stack will look like this. It will consist. Here the stack has 3 symbols. By the way, the stack can grow arbitrarily. It can grow to arbitrary heights. There is no restriction on that. That's why stack is an infinite memory. Okay, and my start state is of course Q. Start state is Q. Initial stack symbol is bottom out of these two, and my rules are like this. If I am in state Q, and if I am seeing left bracket symbol in my input word, and on the top of the stack is bottom, then I replace this bottom by this thing. So if my stack was like this, it had a bottom, and I was state 2, and in my input word, let me draw an input word which consists of, let's say, left bracket, right bracket. So, and I have only one state, so I will always be in Q, so that I don't need to check. So in state Q, if I am initially looking at the left bracket symbol and on the top of the stack is bottom, then what will I do? I will go back to the state Q because I have only one state, and this bottom I will replace by left bracket bottom. So this is what will become the content of my this thing, and this symbol will be gone. I will be at this thing. Now again, if I am seeing a left bracket symbol and on top of the step I have a left bracket which matches with this transition, then I stay in state Q, but I replace the left bracket on the top of the stack by 2 left brackets. So I will get 2 left brackets here, and this is what happens. So as I scan the word from left to right, every time I get a left bracket, I push it on top of the stack. This is the kind of rules that are being given, right? And here is the third rule. Now my head has moved here, so because I have consumed these 2 left brackets. On seeing a right bracket, if on top of the stack there is a left bracket, then I stay in state Q and I replace this top left bracket symbol by epsilon. So I erase this. So my new stack becomes just these 2 things, left bracket, bottom. So every time I see a right bracket, I cancel it against a left bracket which was pushed onto the stack. So you can see somehow, every left bracket is pushed onto the stack and every right bracket is cancelled against a symbol on the stack. And I'm somehow trying to check balance parenthesis. We'll see this automaton clearly, but you get a feel for what kind of automaton there is. So you got an idea of what are the configurations of, what are the transitions of my automata. Now at any point during execution, what will happen? The automaton may be in some state P. The stack may look like this because I may have pushed and popped some symbols, and I have consumed this part of the word already. That's how I reached it at this stack, right? Now at this position, what is the configuration? The configuration is drawn in this figure, but we can also write it in notation like this. So a configuration is a triple. It consists of a stack P, a state P, then the remaining part of so I will have here the state, current state, right? Then the remaining word to be processed. So remaining input, and the current stack, right? This is what I have, right? And this is how I will represent a configuration of the automaton. So in general, a configuration belongs to what? Configuration belongs to Q cross sigma star cross gamma star, right? So the remaining word to be processed is some string over input symbols, and on the stack is some sequence of stack symbols, right? And this is what is a configuration, right? Now given a transition, one configuration will change to another. For example, consider a transition which matches this. So suppose we have a transition which says if I'm in state P and if I'm reading input letter B, which is what I'm reading now, and on top of the stack is A, I will go to state Q and I will replace this A by let us say BC. Okay, this is what I want to do. So what will be the next configuration I will draw? I will not draw it, but I will say that given this transition, I can make a one-step move which will take me to what configuration? Q is the state in which I go. Then this B gets consumed. So the remaining word is what? The first B is gone and I am left with AAABBA, right? That is the word, the rest of the word, because this B is consumed now. And what is on the stack? Well, this A is gone, this top of the stack A is gone, and instead of BC has been replaced. So I will get a BC in place of A, and the remaining stack, this A is gone, this is replaced by BC, and the remaining stack is remains as it is. So B, A, C bottom. This is the kind of new configuration that. So in one step move of this machine, I have written one to say that one step move, this configuration of the stack automaton changes to this. Okay. And what is the starting configuration of the PDA? We always start in the start state. So initial configuration. Initial config of the push down automaton on input word X, which is we are trying to recognize, you'll be in start state. Whole word X remains to be processed, and the stack starts with just one symbol on the stack. This is the initial stack symbol. So you always start with this bottom of stack symbol, the bottom symbol, and then you start processing this. So this is my initial configuration, right? So let me formally define, and we saw from a general configuration which looks like this. If I have a transition rule like this, then what is the change of configuration that happens? What is one step move of my push down automaton? So let's formally look at the definition of one step move. There are two types of transitions: moves on letters and moves on epsilon moves, right? So suppose I have a transition like this in my transition table. My transition will consist of a finite list of such rules, right? Then if my current configuration is like this, it is my automaton is currently in P, and the current input symbol that I am looking at is A, followed by some other sequence of symbols Y. So my input to be processed is of the form of AY, and on the top of stack is A, followed by other stack symbols denoted by this string beta, right? So this denotes my current stack. This denotes my current remaining input to be processed, and my current state is P. Now this matches this transition because the state is P, the current symbol that I am processing is A, and on top of the stack is A. So what do I have to do? From P I go to Q. So my state configuration changes, but P is being changed to this. This A gets processed. So the remaining input to be processed is Y. Now AY, transforms to Y, and this A gets replaced by this gamma, where gamma is some sequence of tape symbols. So what on the top of on the stack we get the sequence gamma beta. That is, we have got gamma at the top and beta below that, right? This is the position of the stack. So this I hope is very clear to you from what we did last time. This is just describing one step move symbolically, right? This is the general case. There are also epsilon transitions possible in our automata. If you are in state P, then you don't look at what is the next. If there is an epsilon transition in my transition table, and at top of the stack if I find an A, so if I have a configuration which looks like that, where current state is P, the remaining input to be processed is Y. I don't care what is the next symbol, and at the top of the stack is A followed by beta. Then if we have a transition like this in our transition table, which says so from P, on epsilon move, silent move, looking at the top of the stack symbol A, you go to state Q and replace the top of the stack A by gamma. So the new configuration you get is this, right? So this should be clear to you. And that is how a push down automaton works. And we will be seeing an example of a run in the next class. We have run out of time, but remember the initial configuration on input word, on input X, which is to be accepted by this automaton, looks like this, right? And we will continue with description of push down automata in the next class. So I hope this is clear to you. Thank you.